In the convexity bound lecture, we talked about this bound that zeta of sigma plus it, absolute value, was less than t to the 1 minus sigma over 2 plus epsilon for sigma strictly between 0 and 1. And in particular, on the critical line, zeta 1 half plus it was less than t to the 1 quarter plus epsilon under the convexity bound. And one might wonder, is this sharp? Is this actually how the Riemann zeta function behaves? And the answer is widely believed to be no. It's expected that this is not sharp. So there is a conjecture called the Lindelof hypothesis. And the Lindelof hypothesis is that actually the absolute value of the Riemann zeta function on the critical line grows more slowly than every polynomial power of t, or every power of t, right? And the Lindelof hypothesis is sort of roughly the same difficulty as the Riemann hypothesis, so it's not going to be proved anytime soon, but it is widely expected to be true. It also applies to more than just the zeta function in the same way that the Riemann hypothesis applies to more than just the Riemann zeta function. Right? A huge class of L functions are expected to satisfy the Riemann hypothesis. That same huge class, as far as I know, more or less, is expected to satisfy the Lindelof hypothesis. And here this is stated just on the critical line, but from this you can extrapolate to behavior in the entire critical strip. So let's say this is going to be 1, this is sort of the axis sigma, it's going to be 1 half. And the Lindelof hypothesis is saying that, this is the same diagram that we used when talking about the Fragment-Lindelof principle in the convexity bound lecture. So this is going to be, say, m0 is epsilon, which is this exponent for the Lindelof hypothesis at 1 half. So it's the power of t that bounds the function. And then, of course, at 1 plus epsilon, you have m1 is 0, right? Your L function is just, for the zeta function, is just absolutely bounded as long as you're to the right of 1. And so what that means, using the Fragment-Lindelof principle, is that the absolute value of zeta of sigma plus it is also at most t to the epsilon when you're between 1 half and 1 in real part. Between 0 and 1 half, you have the bound, again using the Fragment-Lindelof principle with the functional equation for zeta, you end up getting, what's it going to be? It's going to be, so it's 1 half up here. So you're going to get t to the 1 half minus sigma, I guess, plus epsilon. So again, just using Fragment-Lindelof for effectively the convexity bound, or the same principle that goes into the convexity bound, but just on this left half of the critical strip. And this sort of thing, you can do the same thing for other L functions. So one thing I'm going to point out is that there's this area in this field that deals with what are called subconvexity bounds. So subconvexity bounds are when you can prove something like zeta of 1/2 plus it. So these subconvexity bounds are essentially partial progress towards the Lindelof hypothesis. So if you can prove that the the Riemann zeta function absolute value is less than t to the 1/4 minus delta for some delta strictly greater than 0, then you have what's called a subconvexity bound for the Riemann zeta function. And of course, people consider subconvexity bounds for all sorts of L functions, not just the Riemann zeta function. And the significance of this is that this 1/4, this is what we got for the convexity bound. The convexity bound gives an exponent of 1/4. So essentially, if you can beat the convexity bound, that is a subconvexity bound. That is the etymology. The current best the Wikipedia says that it's from Bourgain in 2017. And it is that the on the critical line, the Riemann zeta function is at most t to the, I think it is 13/84. Let me check. Oof. Yes, 1384. All right. So, and this is about it's about 0.1548. Okay. So subconvexity bounds are interesting to a lot of people in this area. It's maybe the single most studied aspect of sort of this theory of automorphic forms. I'm not going to talk about it too much in this course, but if you're interested, then yeah, there's a lot you can read.